Now we're going to look at exceptions to the octet rule. So we've already looked at one. We've looked at hydrogen can have a duet. Lithium, beryllium, and boron also can have less than an octet, and that's not the whole list of who can have less than an octet, because even nitrogen can have less than an octet. But these are the ones we're going to focus on right here. And then we can also have more than an octet, and this happens for elements that are in period 3 and lower, so that's a lot of them. So we're just going to draw some examples here, and we're going to see electron deficient compounds. So less than an octet, we're going to see for the less than an octet, we're going to have an odd number of electrons, and that one unpaired electron is called a free radical. And then we'll look at the expanded octet. So we'll start with BeH2. That was not the right one. Here we go. Okay, so beryllium's going to be in the middle. Hydrogen's on the outside. So then we need our valence. Beryllium has 2, hydrogen has 1, and there's 2 of them, so we get a total of 4 valence electrons. So we put in our single bonds, and that's it. We're done with the structure. So both hydrogens have a duet. Beryllium has 4, but they're okay with that. Next, we're going to do NO2. Okay, so NO2, nitrogen's in the middle, then we have the oxygens on the outside. Nitrogen has 5 valence, oxygen has 6, so we get a total of 17. So we have an odd number of valence electrons. So usually we'll have an even number, but here we've got the odd number. So we put in our single bonds, and then put in the lone pairs around the oxygens to give them an octet. And that was 16 valence electrons. So we have one more. And remember, if you have anything left, you'd put it on the central atom. And so I just have one, so I'm going to put it right there. So both of the oxygens have an octet. Nitrogen has only 5, but we're going to get it as close to the octet as we can. So we're going to make a double bond, and it doesn't matter which oxygen we use. So we're just going to take one of these lone pairs and share it with nitrogen. So now nitrogen has 7, oxygen still has 8. Okay, the next one, BF3. So boron, I think, is the trickiest of all the less than octet exceptions, and I'll show you why. So boron's in the middle, fluorines are on the outside, and then we add up their valence. Boron has 3, and fluorine has 7, and there's 3 of them. So we get a total of 24 valence electrons. So we're going to put in our single bonds, and then our lone pairs around the fluorines. Give all the fluorines an octet. So that's all 24 valence electrons right there. So normally at this point we would say, okay, all the fluorines have an octet. Boron has only 6, so we need a double bond. But that's not the case here. Boron is okay with having less than an octet, so we leave the structure alone. Also, fluorine is in group 7, and it only needs 1 more electron to get to an octet. So everybody in group 7 usually likes to have just 1 bond. There are exceptions to that, but for the most part, group 7 just wants a single bond. Okay, now we'll look at more than an octet. So we'll start with XeF2. So xenon's going to be in the middle, fluorine's on the outside. We need to add up the valence. Xenon has 8, fluorine has 7. So we get a total of 22 valence electrons. So we're going to start with our single bonds and then our lone pairs around fluorines. And that was 16 electrons. So we still have 6 more valence electrons to use. And remember, if you have anything left over, it all goes on the central atom in lone pairs. So we're going to have 3 lone pairs on the central atom like that. And then we're finished. Okay, next we have PCl5. So phosphorus in the middle, and we have chlorines around phosphorus. And we have to add up the valence. Phosphorus has 5, chlorine has 7, and there's 5 of them. So we get a total of 40 valence electrons. So we're going to put in our single bonds here, connect everybody, and then you can put in your lone pairs. Okay, and that is all 40 valence electrons there. So we are finished with that one. So phosphorus has 2, 4, 6, 8, 10 around it, and that's okay. Okay, last one, XeF6. So xenon's going to be in the middle, and then we're going to have 6 fluorines. And then add up our valence. Xenon has 8, fluorine has 7, and that's going to give us 50 valence electrons. So we're going to put in our single bonds, and then the lone pairs around the fluorines. And that is a total of 48 electrons there. So we have 2 left over. So remember, anytime you have anything left over, it goes on the central atom. So I'm going to put that lone pair right there. So we've got 2, 4, 6, 8, 10, 12, 14 electrons around xenon. Okay, so we're going to be looking at resonance structures. And we drew this one earlier, carbonate. When we drew this Lewis dot structure, we said, carbon didn't have an octet, so that's why we made the double bond. And I told you you could use any one of those oxygens to make the double bond. So anytime you get a situation like that where there's multiple places to put the double bond, we have what's called resonance structures. So a double bond is shorter than a single bond. But when they looked at this molecule experimentally, they found that all the bond lengths were the same. So what that means is that double bond gets shared between all the oxygens. So let me show you this one down here. So this structure down here at the very bottom, that's kind of what it looks like. It's a hybrid of all 3 of those structures. That double bond is shared between all the oxygens. But we don't draw it like that in the bottom right. We draw all 3 structures showing where the double bond can go. So let me give you some more examples here. I'm going to draw these 2. Okay, so NO3 negative. Okay, so nitrogen's in the middle, and then the oxygens around it. Nitrogen has 5 valence, oxygen has 6, and we have a negative, so we're going to add 1. So we get a total of 24 valence electrons. So we go in and we put our single bonds, put our lone pairs around the oxygens. Okay, and that is all 24 valence electrons, but our nitrogen only has 6. So we're going to make a double bond, and again, it doesn't matter which oxygen you use to make the double bond. So I'm going to pick this one right here, take those lone pairs and share it with nitrogen. So I have 3 spots where I can make that double bond. That means I'm going to have 3 resonance structures. So anytime we have a resonance structure, we put it in brackets, and then we draw the next structure and put an arrow in between them. So like this. So we're going to draw it again, show the double bond on a different oxygen this time. So just redrawing everything with the double bond in a different position, and then put your brackets. And then we're going to draw the other one over here. So the double bond is on this oxygen now. And put our brackets. And I ran out of room for my chart. Okay, so wherever the double bond can go, that's how many structures you're going to draw for resonance structures. I've got one more example here for you. O3. Okay, so we have 3 oxygen, so I'm just going to put them all next to each other there. So one of the oxygen is the central atom. So we have 6 valence for each oxygen. So we have a total of 18. And we're going to start by putting our single bonds in, putting our lone pairs around the outside oxygens. Okay, so that's 16 electrons right there. And we're going to put the 2 left over on the middle oxygen, but that central oxygen still doesn't have 8. So we're going to need to make a double bond, and again, it does not matter which oxygen we use, so I'm going to use this one here first. Make the double bond. And since there are 2 spots for that double bond, we're going to draw 2 structures. So I'm going to put my brackets and put my arrow here. And then I'm going to draw the double bond on the other side this time. And that's it. So that's it with resonance structures. If you can put the double bond in several places, you just need to draw all the places where it can go.